In this lesson, we're going to be taking a look at a couple transformations that can be applied to different function types. Now to start with, we're just going to be looking at this particular function here, f of x equals the absolute value of x. We'll look and see what the graph looks like and then look to see what happens when we make it into f of x plus 3. In order to do that, we're going to make a table. And this is always a great way to be able to make a graph anytime you're totally stuck on what it might look like. Although you should find that you're not needing to make tables in the actual doing of the lesson or the practice or anything. Really, the tables are just going to be a way for us to illustrate why the behaviors are what they are. And then you just need to know the behaviors. But in order for us to know that, right now, this would be a graph only of x versus f of x. That is, it would just be graphing the original. It would not be graphing f of x plus 3. So we need to add a column to our table here. And so we're going to also have a column for f of x plus 3. Now, in making tables, in order to be able to make a graph, the x values can be anything you want them to be. So I'm just going to pick some basic x values here, ranging from -5 up to 5. If I can see what those are doing, then the rest of it should present itself fairly well. I should be able to tell what's going on. So we're now going to figure out, first up, what is f of x for each of those. So notice up here, of course, f of x equals the absolute value of x. The absolute value of x means take whatever we end up with inside of it and make that final result positive. It strips away the negative is basically what it does. And so the absolute value then of -5 would be a positive 5. And so here f of x just equals 5. And then we're going to do the absolute value of -4, which is 4. And you can kind of see how that's working, right? Now, absolute value of 0 then would be 0. The absolute value of 1, well, it's already positive, so it stays positive. And of course, the rest are going to follow that exact same pattern. Now that we know what f of x is, I can now figure out what would f of x plus 3 be. And so I'm now going to take each of those same f of x values that I just found, and I want to add 3 to it, because that's what this is telling me to do up here. It's telling me to take whatever f of x is and to add 3 to it. And so, for instance, then my 5, it's going to become 8, because I'm just adding 3 to the f of x value. And same thing for the 4, add 3 to it, that brings us up to 7, and we just keep adding 3 all the way down. Now that we have our values, I want to take a look and see what the graphs look like. Now in this case, I'm actually going to plot two graphs because I want to be able to see what the original f of x looked like, and I want to be able to take a look and see what the new f of x plus 3 is going to look like. So since I'm going to be doing them both on the same set of axes, I'm going to go ahead and try to color code them. I'm going to do the f of x in blue, and the f of x plus 3, I'll graph in purple. So first up, for graphing f of x, I always need to be doing x versus y. And in this case, my y coordinate is f of x. And so I'd be plotting the point -5, 5. So we go -5 left, and we go 5 up, and there's that point. And we're going to keep doing that for each of the other points, where, for instance, the next one would be at -4, 4. Once you've plotted all those points, we can see the shape here. And yes, it is that absolute value graph, which is hopefully familiar, that it's going to be that V-shaped graph. And so I go ahead and draw that graph in. And now I can go ahead and move on to the important part, the big part that we really got to get down here, which is f of x plus 3, and seeing what that plus 3 is actually doing to our graph. In order to do that, we again are going to be needing to plot points. But in this case, it's going to be the x coordinate versus the f of x plus 3 coordinate. So we don't really need this stuff sitting here in the middle distracting us here at the moment. So I'm just making that go away here just temporarily for visual sake. And so my first point then you can see would be at -5, 8. So that would be left 5 and up 8. Plot the dot there. And then our next point would be at -4, 7. And so I'm going to go left 4, up 7. And of course, just keep plotting all the points in that same way. And once we've done that, we can see, first of all, that it still looks like the same V shape. Yes, that's always going to be the case. No matter what transformations we apply to a graph, you are still going to have the exact same shape of the graph. But in this case, we can see it's moved a bit. If I draw the graph through those particular points, you can see that it looks like our graph has been moved up 3 compared to where it originally was. And that is actually a very critical piece of information. That's what I want you to be getting out of this most of all, is I want you to see that if I write f of x plus 3 like that, that is a transformation where we are going to shift it up 3. If this had been a minus instead, yes, it would have gone down instead. So, general rule here. Anytime we take our original function and we add or subtract something to the end of that function, it's going to be moving the graph up and down by that same amount. It's the exact same graph, just shifted. All right, now in this particular case, our plus 3 was outside the f of x. But what if we have something that's inside the function like this? So I'm again starting with the same absolute value of x function here. Just this time, I'm going to be graphing f of x plus 2. Notice the plus 2 is inside the parentheses this time, and yes, that is going to change the behavior of our graph. Once again, I'm going to make a table in this case so we can see what's going on. And of course, we already know what the f of x column looks like. That's just the absolute value of x because I use the same parent function. But then the f of x plus 2 column, now we got to dig into that one. So what this is telling us here is that I'm going to take whatever my x value is and add 2 to it, and then I'm going to take that and plug it in for x up in my original function. So I have to add the 2 to x before I do anything else. So I'm going to take the negative 5 here and I'm going to add 2 to it. That gives me negative 3. And so really then what this is going to be is it's going to be f of negative 3. Well, what does f of negative 3 equal? That means plugging the negative 3 in here for x. And so the absolute value of negative 3 is 3. And so that's what's going on here and how we can figure out these values. So let's go ahead and do a couple more of them. So the next one, I'm going to go to x being negative 4. So the first thing I do is I do the negative 4 plus 2, which is negative 2. And then I do the absolute value of the negative 2. And the absolute value of negative 2 is 2. Because the absolute value makes whatever it is positive. And notice, before I take the absolute value, I actually have to do the addition. For a lot of people, they'll think, well, if all that absolute value is really doing is it's just changing whatever this is into a plus. But that's not the case. You actually have to add the 2 to it first and then do the absolute value. All right, let's do one more here. I'm going to go to negative 3 next. So I do negative 3 plus 2, which is negative 1. So then I take the negative 1 and I plug it in for x here. The absolute value of negative 1 is 1. Once I've done all of those, then I have a table that I can actually use to start plotting the points. And once again, I'm going to go ahead and graph both of them here just so I can compare them. We already know the graph of the original f of x function. But now to graph f of x plus 2. Once again, for this purpose, we don't need the stuff in the middle. So just for the moment, I'm going to take that out so that it's not distracting us. And so I'm going to be plotting first the point negative 5, comma 3. So that means go left 5 and up 3 and plot the point. All right. Now, before you start assuming that you know what's going on, we do need to plot all the rest of the points and see what's going to happen here. So next up, I'm going to go to negative 4, comma 2. And I'm just going to keep plotting each of those points in the same way, which gets me to these points. Now you notice if you take a look at those points, it still looks like it's a V shape. Now in this case, it looks lopsided. Why? Because it just happened that we set our x values from negative 5 up to 5. If I had used a different set of x values, then I'd be seeing it a little bit more balanced potentially, depending on what I chose. So there's nothing magical about that aspect here. But I do know that it should be the same shape. because I started with a V, I should end up with a V. So I can go ahead and draw that V-shaped graph now through those points, and I can see what the final result was. Now take a look and see, what did the plus 2 actually do to the graph? In other words, how does our new graph compare to the original? And it looks to me like it was shifted to the left 2 units. And so notice then that if I have x plus 2 inside of the parentheses, it goes left 2. Now, in case you're wondering, what if we had changed our original here? What if instead this had been a minus 2? What would that have changed? Well, remember that the absolute value does not just affect that particular sign in the middle. We would actually have to do the addition and subtraction first and then take the absolute value. And as a result, whereas x plus 2 moved it to the left, x minus 2 would have moved it to the right 2 units. And that's what that would have been meaning. So in general, if I have f of x plus some number, that means that it's going to be shifted left that number. And if I have f of x minus some number, that will shift right by that number. So notice that when we're shifting left and right, it's kind of counterintuitive, because when you see this minus here, the negative direction on the graph is to the left, of course, but it doesn't do that. So it does not operate exactly as logically as you might think, because we're actually shifting it sideways. All right, and to do one last problem to kind of see how all this stuff works, we're going to take a look at how we would do this one. Notice this time, I've now given you a different original function. In this case, f of x equals x squared. All that's going to change is what the original function looks like. But the behaviors of it will still be the same. So as we go over here to transform it like this, you're going to find that the 5 and the 1 do exactly what they would have done if it was absolute value or any other function type that you've seen or that you haven't seen yet. So let's go ahead and take a look first at just what would the graph of f of x equals x squared look like. So x squared, that's our basic parabola graph. It's that U-shaped graph. If you're ever not sure about it, you can always just say, well, I'm squaring it, right? So 0 squared is 0, so I go over 0 up 0. 1 squared is 1, so I go over 1 up 1. 2 squared is 4, so I go over 2 and up 4. And y squared, because this is x squared here, that's telling me what to do to it. And then if I go over 3, I would square 3 to know that I go up 9. And we could do the same thing on the left-hand side, because negative 1 squared is a positive 1, negative 2 squared is a positive 4, and negative 3 squared is a positive 9. And so I can plot those points and draw the nice pretty curve that goes through them. Now that I know what the original graph looks like, though, I now need to be able to make the graph of my transformed function here. And so the first thing I want to do is just identify what do each of the parts of this function do. So the x minus 5 here, notice the 5 is in the parentheses with the x. We saw that earlier. We saw that whenever it's in the parentheses with x, it moves it in the x direction. And specifically, we also saw that minus moves it to the right. So this tells me that I'm going to be taking my graph and I'm going to be moving it right 5 units. Then we have this minus 1 hanging on the end. When we saw the number hanging on the end before, that moved it up or moved it down. A plus moves it up, a minus moves it down. This one is intuitive. This one does happen the way you think it should. So the minus 1 here will move our entire graph down 1 unit. And once we know that, then we can go ahead and make our graph, because it's going to be exactly the same as the graph that I have here, except that it's going to be moved to the right 5 and down 1. So let's do that. So notice I got a point right here at 0, 0. I'm going to take that point and I'm going to move it to the right 5 and down 1. And so that point that was at 0, 0 is now going to be there. I kind of like to think of this as my starting point. Remember how in order to plot the graph of x squared before, I started at 0, 0, and then I said, well, 1 squared is 1, so I go over 1 up 1. And 2 squared is 4, so I go over 2 and up 4, and so on. All of the points are in the same relative position. That is, they're in the same places when compared to our starting point. So once you have that starting point, you can go ahead and just make the graph like you normally would for x squared. Draw the curve through those points, and you're done. Now, just one little detail here. In each of these graphs, I had you plot both graphs as we did it. The original one, where I plotted just f of x equals x squared, for instance, in this one, those graphs were there just so we could talk about the starting point. When you are actually making these graphs for the assignments and things like that, the only thing that you need to graph is just the transformed graph. You do not want to include the other one as well. That's just been a teaching tool that we've been using as we look through this.